This video today is going to be a quick TensorFlow crash course. My goal is to teach you TensorFlow easily, simply by actually building stuff. We're going to do one regression example and one classification example, actually the other way around, first the classification, then the regression. And while doing that, we're going to discuss the different classes, functions, and components that we use. So this is going to be very practical and targeted towards beginners. If you like this video, let me know by hitting a like button and subscribing, but now let us get right into it. Alright, so we're going to do a quick TensorFlow crash course in this video today. For those of you who don't know what TensorFlow is, it is a Python library / package, you could say, for deep learning, so for machine learning with neural networks. They call themselves here an end-to-end platform for machine learning. The basic idea is you have this backend, this low-level backend, which is a little bit like NumPy, you could say, called TensorFlow, and on top of it you have a high-level API for deep learning called Keras. Now, Keras does not have to belong to TensorFlow, but most of the times nowadays when you're talking about Keras, you're talking about Keras on top of TensorFlow. That is like the quick little theoretical introduction here. In a nutshell, we're building deep neural networks here in Python using TensorFlow, which is a package by Google. An alternative to it would be something like PyTorch, which is nowadays the more modern or the usual thing that people choose when they do research or projects, but we're going to do TensorFlow in this video today. So let us get started by setting up our environment. For this, I'm going to open up a terminal here, and I'm going to navigate to a directory where I want to be coding in. So in my case, that directory is the tutorial directory, and in here now I'm going to set up my project. Now, how you do that exactly on your system is up to you. You can just use your basic Python installation if you have it on your system. You can do pip or pip3 install, and then all the packages like TensorFlow and so on. Or you can build a virtual environment. You can create a virtual environment by using the default venv tool, so python-m venv.venv. What is the purpose behind this? The idea is you create a virtual environment to have an isolated environment where you can install packages. They don't interfere with the Python packages of the system installation. This is usually recommended when you do some sort of new project. Just create a virtual environment. So create it, activate it, and then install the packages in there. Or if you want to go the more modern route, you can also use UV, which is a Rust-based Python package manager. If you want to use UV, you first need to install it. You can also do that with pip. So you would say pip or pip3 install UV. And then once you have UV on your system, you can just say UV init to create a new project, and then UV add instead of pip install. Now, for your purposes here, whatever you want to do, do it, but you need to install the packages. So either pip install or UV add the following packages. The most important one obviously here is TensorFlow. Now, it's important that we also add here in square brackets, if you have a CUDA GPU, so an NVIDIA GPU, and you want to use this GPU for machine learning, you want to make sure that you also specify here and-CUDA. And in my case here, I have to put this in quotation marks. This will install now TensorFlow with the CUDA packages as well, with the NVIDIA packages that are necessary to use the GPU. In addition to that, I'm also going to install scikit-learn. I'm also going to install pandas. And actually, I think that's it. I'm not sure NumPy should already be installed by the other packages here, but these are the ones that we're going to need today. Just make sure you have them. So again, pip install or UV add. And one more thing that we're going to need here, this is now optional, but I highly recommend you also install this, is JupyterLab. This is the environment that I'm going to use. I'm going to work in interactive Python notebooks here today. So you can either use Jupyter Notebook, which comes with Python by default. You can use VS Code to read the notebooks or to write the notebooks. In my case here, I'm going to use JupyterLab. So I'm also going to say here UV add JupyterLab, or in your case, if you're not using UV, pip install JupyterLab. This is going to allow you to get this onto your system as well. Now, once you set everything up, just start JupyterLab. How do you do that? Either you just go JupyterLab like this. This works if you're not using UV. And in my case, I have to say UV run JupyterLab to make sure I'm using the environment that I'm currently in here. Now, let me beam away this terminal and let me get my browser that just opened here on localhost. Now, this is JupyterLab. A very brief introduction for those of you who have not worked in this environment before. The basic idea is we have interactive Python notebooks. So if I open the files here, I have my default Python file. That here is just a Python file. I can delete this. A notebook looks slightly differently. So in Notebook, the basic idea of an interactive Python notebook is that you have individual cells. Let's call this one main IPYNB. And the idea is I can run here a equals 10 as one statement. I can say print a in another cell. Then I can say a plus equals 10 to increase it by 10. And then I can print again up here and I get 20. So these run as individual cells, which means that if I do the data pre-processing here, train a model here, and then use the model here, and then I want to change something and use the model again, I don't have to run all these cells again. I can just change something here and run it again. That's the basic idea. And usually when we do machine learning or data science stuff, it makes sense to work with interactive IPython notebooks. So let us get started now with TensorFlow. What we do first is we import TensorFlow as TF. This is the usual alias that we use. Now, what you can see here is just an info message. If for some reason you also see here a text telling you that CUDA is not being used, then probably you didn't install it properly. If you see something like CUDA is not being used because the packages were not found, or I don't know what the exact error message is, then you probably have to run the installation with &CUDA, or maybe you don't have a GPU that supports CUDA. That's also a possibility. In this case, it would fall back to the CPU. So now what we're going to do as a first example here is a simple classification task. Now classification means there is some input data and at the end we need to say it's either this or that or something else. So we have certain classes and we need to decide which of these classes is the correct one. So a simple one would be a binary classification, yes or no. Is this a cat or is this not a cat? Yes, no. Or you could also say, is this a cat or a dog? Cat, dog would be the two classes here. In our case, we're going to work with 10 classes because we're going to do simple handwritten digit recognition, which means we're going to get the MNIST dataset. This is a dataset containing images of handwritten digits, 28 times 28 pixels to be precise. And our goal will be to take these images and to correctly recognize the digits inside of these images. So this is a 3, this is a 9, this is a 0, and so on. And we're going to do that using a neural network. So for this first data set, we're going to go the easy route and we're going to load it directly using TensorFlow. Later on, I'm going to also show you a regression example. The goal of regression is to predict the values, so it can be on a continuous spectrum. And there we're going to actually load the data from a CSV file, so from external data, from an external data source. But to keep it simple now, we're just going to say MNIST, which is the name of the data set, is equal to tf.keras.datasets.mnist. So right now this is an alias. MNIST is equal to MNIST, the MNIST module. And I can now call from this MNIST module the function load data. Now the interesting thing about this function is that it already returns the data properly split up into training and testing data. For those of you who don't know a lot about machine learning, maybe this is the first time you're encountering machine learning. In this case, actually, I would recommend learn traditional machine learning like scikit-learn, or in the Python context, scikit-learn, or in general, learn about k-means clustering and linear regression and so on. But for those of you who don't know what a train test split is, the idea is you have your whole data set, all of the data that is available to you, and you want to reserve one portion of the data, 80% usually, for training the model, so for teaching the model how to correctly classify digits, and you want to take the remaining portion, the 20% usually, to then evaluate the model once it's trained on the unseen data to see if it performs well on data it has never encountered before. That is the basic idea of a train test split. We can now say here x train and y train is the first tuple, and x test and y test is the second tuple, because that is exactly the structure we get here from a call to load data. So if I run this now, you will see that I have x train, which has this shape here, or actually I can also just say dot shape, and it will tell me, okay, I have 60,000 images with 28 times 28 pixels. That is how you can read that. Now for y train, the shape is a bit different. The shape is 60,000, but just one value, which is the digit. So I can take, for example, the first pixel collection that I have here, and you can see these are values between 0 and 255. Why? Because we only have the lightness value. This is grayscale. We don't have colors. And this basically means 0 is completely black, 255 is completely white, and everything in between is basically gray, different shades of gray. 255 shades of gray, to be precise. Unless you count white and black, then you would have two less, but you get the idea. Now, since we're working with neural networks here, we have something that is scale sensitive. Neural networks are scale sensitive. They're not like decision trees. They're not like random forests. They actually cannot really handle, or it's hard for them to handle data on different scales. So it makes sense to normalize the data here. So we have values between 0 and 1. It's just more convenient to work with. And for specific data sets, it's even crucial that you do that because you have different features that have different scales, and this can really confuse the neural network. So what we're going to do now, very simple, is we're going to take all these pixel values and we're going to divide them by 255. This is called a pre-processing step. The idea is that I'm taking the data and I'm bringing it into a format that I want to be working with when I do the deep learning part. So I'm going to just say xtrain and xtest. We're not going to do the same thing for the y data. Is going to be xtrain divided by 255 and xtest divided by 255. So this is just normalizing the data here. Now, if I take a look at the first example, you can see that I only have values between 0 and 1. So easier to work with for the neural network. Now, for the y data, we don't need to do that because these are just classifications. So if I take a look at ytrain, I can just see these are the digit numbers actually. So the first image represents a 5, the second one is 0, and so on. So we don't need to do any scaling or any normalization here. So right here, we don't really have a lot of TensorFlow stuff yet. I mean, yes, we used the data set from TensorFlow, but then we just did an ordinary division. Now we get to the part where we actually do the deep learning. Now we're going to build a model and we're going to take this data as training data. We're going to teach the model how to recognize digits, and then we're going to evaluate the model. And while doing that, I'm going to explain the various components. Now, it's important here to highlight that similar to my scikit-learn tutorial, I'm not teaching you the actual algorithms. So in my scikit-learn tutorial, I also didn't teach you k-nearest neighbors or linear regression or k-means clustering or whatever. I just taught you how to use scikit-learn to apply these algorithms. In a similar manner, I'm going to show you here how to use certain layers, but I'm not going to go into detail on the different activation functions and the different parameters that we use. I'm going to briefly mention what they do, but I'm not going to focus too much on the theoretical side here. That is something that I would cover in a separate crash course on the theory itself. But to keep it simple, what we're going to do now here is we're going to do some imports from TensorFlow Keras. So from tensorflow.keras.models, we're going to import the basic model type that we will use most of the time, sequential. So this is just a simple feed-forward neural network, a simple sequential neural network. And in this neural network here, I want to have different layers. And these layers are from TensorFlow Keras layers. And it depends, of course, now on what you want to build. So our use case today is quite simple. We have some pixels and we just need to predict the digits. For this, an ordinary dense layer, as it's called, fully connected layer, or also linear layer, so just a couple of neurons connected with weights and biases, that is enough to achieve what we want to achieve here. But if you have complex images, for example, or you need to do some complex tasks on images, then probably something like a convolutional neural network where you have kernels, filters, you have features that are being extracted on a local level and then maybe aggregated, and then you have max pooling layers. That would be a more suited architecture here. But we're going to keep it simple. We're going to start with the most fundamental layer here, which is the dense layer. The dense layer is called, for example, in PyTorch, the linear layer. It's also oftentimes referred to as a fully connected layer. It just means we have neurons in one layer, we have neurons in the next layer, and they're just connected with connections, with edges, so to say. And these connections have weights, and the neurons themselves have biases. Very, very simple, the most basic form of layer that we have here. We're also going to need a flattened layer. This is like a transformation. We get this 28 by 28 structure, and what we get out there is 28 times 28. We get 784 neurons from flattening the input, so to say. Then also, since it's a best practice now to use the input layer, we're going to use an input layer. This is basically the same as using the flattened layer directly, but providing an input shape. It's just nowadays the correct way to do it, just use an input layer. Then also we're going to use a dropout layer. A dropout layer is mainly used for regularization. The idea is that you don't want the model to rely too much on individual connections. So what you do is you add a probability for every single connection to drop out, to not be there in this iteration of the training. So basically you're saying, okay, if this connection is not here, you still need to perform well. So you make the model more robust, you could say. You also prevent overfitting. You're not allowing it to rely on connections always being there. That's the basic idea. And these are actually the layers that we're going to use now for our model. How can we define a model in TensorFlow? Quite simple. I can just say model is equal to sequential, and now I can either pass the layers as a list, so I can do something like this and then just add the layers like dense layer and so on, or I can add them afterwards. I can say model is sequential and then model add. Both is fine. Choose whatever you like more. We're going to start here with an input layer. So how do we choose here the parameters for input? As I already mentioned before, our data has the shape 60,000 samples, 28 times 28 pixels. So we need to say, okay, one instance of the training data has 28 and 28 as shape. So this is my input shape. I'm going to pass it here as a tuple, 28 times 28. That is what I get into this neural network. And I think I'm missing a bracket here. And in the next step, I want to take this and I want to flatten it. I want to make it 784 neurons or data points, you could say. So I'm going to say here, just a simple flatten layer. Then in the next layer, I want to do the actual reasoning. I want to actually have the intelligence in a single layer here. We're going to keep it simple. And I'm going to say model add dense layer. And for the dense layer, now I need to specify the number of neurons. The more neurons I have, the longer I have to train, the more complex the layer is, the more stuff I can do, the more parameters can be tweaked, but also the more I can overfit the data set. So I can say here 64 as a reasonable number for this simple task. And then, of course, we can increase it or decrease it and see if it works. This is also a so-called hyperparameter. These are things that we can tweak to see if the model can perform better when we change these parameters. Now, what's very important is you need to break linearity. I have a video on this channel which is quite well liked by you guys called why, or I think something like why we need activation functions. And there's a mathematical explanation where I show you guys why we need to break linearity. Because otherwise, if you don't break linearity in a neural network, you just have a simple addition multiplication chain, which is a linear combination of the inputs, and it's not very intelligent. You cannot model any nonlinear relationships. So long story short, what we need to do is we need to provide an activation function for this dense layer. And this activation function, in my case here, is going to be a simple rectified linear unit, ReLU. There's also other functions that we can use here. ReLU is the most simple one. It's basically just any number that is below 0 outputs 0, and any number that is above 0 outputs the number. So you basically have this shape here, if you see this in the camera. So you have nothing or always 0, and then you have like whatever the number is. And this thing here is the break of linearity, linear, nonlinear. And that is what you need in a neural network to make it work. Then what we're going to do next is we're going to add the regularization layer, which is the dropout layer, and we're going to say drop out how much percent or what should the likelihood be of a connection disappearing in a certain iteration. I will say 20%. So I have a 20% chance that a connection will not be there when we do a new iteration. And then we can also say, finally, this is now important, this has to be this specific number. We're going to add another dense layer. This is going to be our output layer. And here we need exactly 10 neurons. Why? Because we have exactly 10 digits, and every neuron is going to represent the probability that this particular digit is the correct one. So if the digit is 0, the first neuron of this layer should have the highest activation. If it's 1, the second one should have the highest activation, and so on. Now, we could theoretically also add softmax here as the activation function, but this can result in numerically unstable loss calculations, so I'm not going to do that. What I mean by that is the following. Let us create this model now. And let's just feed any data into this model, because this model now, of course, is untrained, but it does have some parameters already. It does have its structure already. So we can say here nonsense prediction is equal to model being applied to some input data. So just call the model on xtrain and call it on the first sample. I'm using slicing here to have an additional dimension, and then get the result as numpy. And then, of course, show this result. That is the prediction that we get. Now, this prediction here is nonsensical, and you can see that this is the case because we can also calculate the loss, and we can also see that these values are pretty random. The actual value that we get when the model is trained will be most of them being pretty low and one of them being pretty high, which is going to be the preferred guess, so to say. But what you can see here is that when we add all these numbers up, we're most likely not going to get 1. So these are not 100%, and these are not percentages in general. These are so-called logits. This is just the output of the neural network. The softmax function would now take these values and make sure that they all are probabilities that add up to 1, so to 100%. The problem with softmax is that it's numerically unstable to do the loss calculation. So what we're actually going to do is we're going to do the loss calculation on the logits, and then we're going to apply softmax just for the inference, for the reasoning part. So just to maybe show you how this works, I can say tf.nn softmax, which is the function, and I can feed in here the nonsense prediction, and I can get the output, and now this is the difference. All of these are positive, and all of these add up to 1, add up to 100%, which I think if I do dot sum, there you go, it's basically 1. Now, before we move on with the training, I would like to also show you that this output is pretty random. We can prove that actually by using a loss function. So I can say here from TensorFlow .keras.losses import the sparse categorical cross entropy, which is classic for these classification tasks here. And I can just say the loss function I want to use is this sparse categorical cross entropy. I'll also specify that the input here is going to be from logits. So from logits equals true. And then I can take this function and apply it to the output, so to this nonsense prediction here, and I can also compare it to the ground truth, which is going to be Y-train, first example, because we do know what the actual answer is. But before I do that, I also want to show you that we can predict what the output should be if it was random. So if this is random, if we have actually random predictions, we should have 1/10 for every, or 1/10 likelihood for all of these outputs. So that should be pretty equally distributed. So I would say 1/10, and then I would take the negative log prop. So I would say minus tf.math.logarithm of that. This here, the negative logarithm of the probability, should give me the loss that I'm expecting. So the loss I'm expecting here is 2.3 calculated here. This is exactly what I'm expecting if it was perfectly random. It's not going to be perfectly random, of course. It's not going to be perfectly equally distributed, but it's going to be quite close to that. So we can just say here, apply the loss function to the nonsense predictions, or actually I think first we specify Y-train up until 1 in the nonsense prediction, and you can see we get 2.12. which is pretty close to 2.3. Cool. So to recap, we have our data, we normalized our data, we defined our model, we have 10 output neurons that produce some logits that look like this. We can apply softmax to get the actual probabilities that look like this. And we're only going to use that to take a look at the probabilities. For all of the training, we're going to use just the basic logits here. We have a loss function that calculates how wrong we are. And then what we're going to do now is we're going to compile the model and train it. Now, what does it mean to compile the model? It means that we define an optimizer, we specify the loss function, we choose metrics to take a look at, and then we just make the model ready for training, so to say. And for this now, we need an optimizer. So I'm going to say here from TensorFlow.keras.optimizers, import the Atom optimizer, just like the classic choice. And what does the optimizer do? The optimizer is the thing that actually takes the steps. So backpropagation is the process of calculating and backpropagating the losses. So the loss function produces some loss, and then you can use the chain rule of calculus. This is the theory now behind the scenes. You can use the chain rule of calculus to see which parameters influence this loss in what way, and then you can take steps in the opposite direction. So in the direction of the steepest descent. And the optimizer does that in a different way. If you have a stochastic gradient descent, SGD, you would just do it like this. You would just go into this direction, and that's it. Atom has some more stuff like momentum and so on. But essentially, we just define an optimizer. We provide a learning rate to this optimizer. So learning rate is the parameter. This is like the intensity with which we go into this direction that decreases the loss. I'm going to go with 0.01. And then we're going to say model.compile. Optimizer is equal to optimizer. Loss is equal to loss function. And metrics are equal to accuracy. It's So this is now ready to train, and training is super simple here. We don't need a training loop like in PyTorch. We can just go and say model.fit. Fit trains the model now on the data, and I provide the X data, the input data, the pixel, so to say, and the ground truth, the correct digit classifications. And one more thing, I need to provide the epochs, the number of times the model is going to see the same data. So we want to feed the same data over and over again to the model so it can further optimize on this data. And in this case, I want to say epochs is equal to 10. So I'm going to run this. This prints some warning, and now we can see how this is training. We can see that the loss is decreasing. Now, if you see that the loss at some point is increasing, or actually for this, we should probably use a validation set. But if you see that the loss is maybe not decreasing enough, or it's kind of jumping around, then you know you don't need to necessarily train further. If you see it going down and down and down continuously, there is a balancing act because you can optimize on the training data. But the reason you want to use validation or testing data is because you want to make sure that the model actually performs well, not only on the data that it optimized on, it also performs well on similar data that it didn't see before. That is the balancing between training a lot, overtraining maybe, or overfitting as it's called, or generalizing well. So sometimes a worse performance on the training data can mean a better performance on the testing data. This is what I'm trying to say here. So now the model is trained, and we can just go ahead and say model.evaluate to see how it performs on unseen data. So now I can say X test and Y test. And running this now gives me a loss of 0.21 and an accuracy of 95.7%. This means from all the images that it saw, it correctly classified and recognized the digit 95.7% of the time. Now we can see if we can improve that performance by increasing, for example, the number of neurons in the dense layer. If I go with 128 and I do the exact same thing, will I end up with a better performance? Now, trying this stuff and adding more layers and changing the parameters is called hyperparameter tuning. You can do that manually, you can do that systematically with different packages, but these are hyperparameters. Also changing the activation function, for example, would be a hyperparameter, and they can lead to better performance. Now, one thing that you need to keep in mind, though, is if I do this now with the training data, in this case, you can see it worked. I got 96.31% accuracy here, so this is better. But you need to keep in mind that if I tune now using this testing data set, I'm actually not using it correctly, because what I'm doing right now, this hyperparameter tuning, should be done with a third portion of the data, which is the validation set. Which means that this is what I use to tune the hyperparameters, still unseen data for the model, but I'm using it to tweak the model for optimal performance. The testing data should be reserved up until the very end to just give it a final test to see if the model performs well on completely unused data. Means not seen by the model and not used by me for hyperparameter tuning. But let's try one more thing. Let's try to take this and add one more dense layer with 64 neurons, for example. So now we're making the model more complex, more deep, you could say. And now, of course, this will also take more time for each epoch now, and we also have more parameters. But let's see if this actually now outperforms the previous models. In this case, not. In this case, it underperforms the previous architecture. But again, this doesn't have to be the case. It doesn't mean that this is actually the better that the previous one was actually the better configuration. Maybe you also just need to train this for longer. So yeah, it's a lot of trial and error, and it's trying to come up with an architecture that can fit your use case. So I would guess that something like this is probably a pretty good architecture. Using convolutional layers would be even more effective in this particular case because we're actually using features, local features, and we're aggregating them at the later levels. So that's a simple classification example. Let's briefly recap. We load the data directly from TensorFlow. We already get a train test split. We have this shape. We normalize the data so it goes between 0 and 1. We only do that for the pixel values. Then we define our architecture. We choose the simple sequential model. We have the input shape of 28 times 28 pixels. We flatten this shape to be 784 data points. Then we have a reasoning layer here, so to say, a fully connected dense layer, 128 neurons, breaking linearity with a simple ReLU activation function, having a 20% dropout chance for the individual connections, and then producing the logits, 10 logits to get the actual output. Then we have here the default predictions. We can apply softmax to actually get the probability. we have a loss function here, we have an optimizer, we compile the model using this loss function optimizer, we train the model, we evaluate the model on unseen data, and it has a certain performance. Maybe final thing, we can also say model applied onto X test up until 1, and now we can see that this here produces the logits, and then I can say tf.math or tf.nn softmax applied to this dot numpy to get the actual value. That produces these outputs from softmax. And what I can also do now is I can use argmax. So tf argmax like this. And this will give me, actually I need to provide the axis 1. This will give me the 7. So that number is a 7. Let's see if the test data actually agrees with that. The ground truth, it's a 7. So argmax basically gives me the position with the highest activation. If we just look at the raw data again, we will see that the number 7, or the index 7, which is the number 6 actually, the digit 6, will have the correct activation. Or actually index 7 is also number 7, sorry. Index 7 is obviously also digit 7 because we start at 0 and we also start counting at 0. So that actually is the highest activation here, almost 100% for 7. Now let us move on to a regression task. For this, I'm going to use a markdown field here. I'm going to say regression task because this is now a different approach. On the one hand, we're going to load the dataset from a CSV file with pandas. We're going to do the pre-processing with scikit-learn, and we're going to then have to figure out what architecture can work with the data and what loss function we're going to use here. So that is now a different use case for a different sort of task. To recap, a regression task is where you predict not a class. So you're not saying this is either a cat or a dog, or this is something like, I don't know, a digit 1, 2, 3, 4, 5. But this is actually now on a continuous spectrum. So you're saying, give me the price of this laptop, give me the price of this stock, or give me the probability that something is the case. In our case, we're going to do this with house prices. So I have here a CSV file, housing.csv, and I have a bunch of information in here, as you can see, not pre-processed, so we don't have, or at least not scaled. We don't have everything here on a normal distribution. Or at least the values here are not scaled in any way. The values here are not scaled. The values here are not scaled or normalized. But what you can see is we have the target value, the median house value of the particular area. We have some coordinates. We have occupation, number of bedrooms, average number of bedrooms and rooms, and the house age and all that. And our goal is to take these information pieces here and to predict this with regression and with neural networks. So let us get started by using pandas. I'm going to say import pandas as PD. By the way, you will find the code for this video in the description down below on my GitHub, and including the dataset as well. So as a CSV file, this is just exported from scikit-learn. So nothing too fancy here. We're going to say here data frame is equal to read CSV. So pandas read CSV, and we're going to load the housing.csv dataset. This is what it looks like. And now, since this is not returned to us as already xtrain, ytrain, xtest, ytest, we need to do it ourselves. So we need to define what is x and y. We need to define what is xtrain, ytrain, and we need to also scale the data. So I'm going to say here from scikit-learn, so from sklearn.model selection, import train test split, and then from sklearn.preprocessing, import the standard scaler. Then we're going to create the scaler. I'm going to say scaler is equal to standard scaler, just like this. I'm going to say x and y are defined as follows. df drop, the target variable, is going to be x. So everything except for y is x. And this is the, what was it called? Met house value, like this. And we're dropping axis 1 because we're dropping a column, not a row. And y is basically just that. So y is df median house value. Then I'm going to take x and y and I'm going to split them into train and test data. So I'm going to say xtrain, xtest, ytrain, ytest. Notice that this now is a different order. Now we have xx and yy, and up there we had, for TensorFlow, we had train, test, test. So this is a different order here that we get from scikit-learn, but we're going to say that is equal to train test split X and Y with a test size of 20%. So 0.2, 80% for training, 20% for testing. Now we also need to scale the data. So I'm going to say xtrain scaled is equal to scalar dot fit transform xtrain. And then we're going to say xtest scaled is equal to scalar transform xtest, because we're not going to fit again. We fit on the training data and we just apply also on the testing data. This is realistic because you can only train the scalar on data that you've already seen, and you have to reuse it with the learned parameters on data that you've never seen before. Now, what does our data look like? I can say xtrain scaled, and this is what it looks like. A bunch of values, a numpy array essentially, that we can easily feed into a neural network architecture. And this architecture is going to be quite simple. The only thing to consider here is the shape of the input. So if I say dot shape here, you can see a bunch of examples with 8 values each. These are the 8 features that we had in the beginning, these here, and these are what we feed into the neural network. So I'm going to say here again, model equals sequential, model add, and the first layer here is going to be an input layer again. But this time the input shape is just 8, comma. So we just have 8 values, comma, to make it a tuple, because otherwise it's just an integer in parentheses. Here now this makes it a tuple, input shape is 8. Then we're going to feed this data into a dense layer. So dense layer with 64 neurons, activation function will be ReLU. Then give me one more. And then finally, our output layer will contain also a dense layer, or will be also a dense layer. But this time we're just asking for one value. We're just asking for the price. And that is just a single neuron I need here. Now, important, the activation function you choose here is relevant, because if you choose softmax as an activation function, it doesn't make a lot of sense. If you choose something like sigmoid, you cannot get any values outside of 0 and 1. So you can only get values between 0 and 1. But since we want to predict the price, just take the raw output as the truth, so to say. So that's going to be our architecture. Now I'm going to say again, model compile, and we don't need to always pass instances in TensorFlow to the compile function. So I can, for example, also say optimizer is equal to Atom, like this, without passing an instance of Atom. And the same for the loss function. I don't need to say the object is loss of n, which is sparse categorical entropy. In this case, we're going to use the MSE loss, the mean squared error loss, but I'm going to say just MSE. So I'm not actually going to use the MSE object, or I'm not even sure if MSE exists in TensorFlow. I'm just going to provide loss is equal to MSE. And the metrics I'm interested in to monitor the process. Now, MSE is very convenient for training. This is a function that can easily be differentiated and is very convenient for just using it as a loss function to backpropagate the loss term. But for metrics, for monitoring the process, I actually prefer to look at the mean absolute error, because this is more interpretable. And I also want to look at R squared, or R2 score. So that is the compilation. Now model.fit xtrain scaled ytrain. And of course, not a single epoch, but let's go with 10. Now I'm going to do epochs, sorry. Now I'm going to actually do 11 because I already did one. But you can see how the R2 score is increasing, at least up until this point here. And the mean absolute error is going down, at least for the most part. Yeah. So it looks like 10 epochs are maybe even too much. But let's go ahead now and say, I want to evaluate this. How do I do that? I say model evaluate xtest scaled ytest. This is going to give me the 3 values. I'm getting a loss. I'm getting so the loss is the MSE, I'm getting the mean absolute error, and I'm getting the R2 score. If you don't know what these metrics are, I have a detailed video about evaluation metrics for classification and for regression. There you can see when to use what and what they actually mean. But maybe to get an understanding, we can say, give me the data frame and describe the median house value. So I can just say describe here to get statistical information. And I get a mean absolute error of 0.37. And this is actually for a feature where the mean is 2 and the standard deviation is 1.15. And yeah, it's not perfect. It's still a pretty large error loss, but it's at least something. So we do get a decent performance, but it's actually not really that good in this particular case. What I want you to learn from all this, these were just two simple examples, is that this is how you use TensorFlow. You load data in some format. Sometimes you will load it from a TensorFlow dataset. Sometimes you will load it from a CSV file using pandas. Where is it? Down here. Sometimes you will load it from some web tool. Sometimes you will load it from a JSON file, whatever. You get some data into your program. You do some pre-processing. At the end, you want to end up with xtrain, xtest, ytrain, ytest, and you want to have NumPy arrays or tensors, TensorFlow tensors, that you can feed into your model. You then need to choose an architecture where the input shape is the right one for the data that you're feeding into it. Here it was 8 because we have 8 values per sample. Up here it was 28 times 28 because we had this shape for the data that we got. And then you just have some logic in between. Here you need to be sure that you know what you're doing. Dense layers are simple to just stack on top of one another. You have convolutional layers that usually you want to follow by max pooling layers. Maybe you want to have some batch normalization in between. Maybe you want to have some dropout in between. This goes more now into the theory side. But once you have your architecture and the output layer, which has to be whatever you're trying to predict, in this case 1, because we're guessing one value, one price value. Up here it was 10 because we want to have the probabilities. Where is it? We want to have the probabilities for 10 different classes. In a sense, you could argue this is also a regression task. We're doing regression on the probabilities here. This would also be a fair assessment. And optionally, you can then apply also an activation function on that to get different sorts of values. And then you can evaluate the model and also use it on unseen data. This was just a crash course. It was not super detailed. I tried to cover the most important stuff when it comes to TensorFlow in a short amount of time. I wanted to keep it practical, I wanted to keep it quick, and I wanted to keep it intuitive. There's much more to learn, many different architectures, many different functions. There's also a low-level TensorFlow ecosystem, you could say, or the platform, the low-level backend of TensorFlow, which is where you can work with the tensors, where you can do all the shuffling and all the pre-processing, which I didn't cover today. This is a more advanced thing, even though it's, you could say, the fundamental part of TensorFlow. But I hope this video helped you guys to understand the very basics quickly. So that's it for this video today. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. Also, in case you're interested, on my website, you will find a services tab and a tutoring tab. On the services tab, you can see what I have to offer as a freelancer. On the tutoring tab, you can book me for one-on-one tutoring, teaching you stuff one-on-one. And on both pages at the bottom, you will find a mail and a LinkedIn icon where you can contact me if you're interested. Besides that, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video and bye.